Enumeration is just a fancy word for counting. So when we say we want to enumerate the number of objects, we're really saying we want to count them. So one of the groups that we might be concerned with is called the population. Now the population is the entire group that we might be concerned about. So if I wanted to, say, find out how many Americans there are, my population is Americans. All right? If I wanted to figure out how many water buffalo there are in the world, then my population is water buffalo. Right? So one thing I might want to know is just how big my population is. How many people or animals or objects are in my population? So to find that, I can use a variety of methods, but one of them is conducting a census. Now we've heard that word too. The US is in the middle of one of their censuses right now. Census for the US gets conducted every 10 years. And we don't do it any more often than that because it's very costly to conduct. So why is that? Well, a census is individually counting every single person or animal or object in the population. So for the United States to conduct a census, they are individually counting the millions of people who live in the United States. As you can imagine, a census is not always a practical thing to do, depending on the size of our population. One of the ways that we can get around this, and people who work with wildlife often use this technique when they're trying to approximate what a population of a species is. They'll capture a sample of that species, they'll put a tag on each member of the sample that they've captured, and then they'll release them back into the wild. And after a while, then they'll recapture another sample. And that sample won't necessarily have all of the tagged animals that they found, but it'll probably have some tagged animals. And then they set up a proportion that sets up how many tagged animals there are to the total number that they had. And from that, we can approximate a population. So we're going to do that right now. Let's take a look at an example. All right, so let's say we want to know the population of some fish in a pond. So I'm going to catch a sample, my first sample, of 200 fish. And on each of those fish, I'm going to tag them. So they are tagged. Now say I release them back into the wild, and after a little while, I collect a second sample. I catch a second sample of fish. I have 150 fish in this sample, and 21 of those have tags. Now, if I think about the relationship to my fish population in my pond, I know that 200 out of all the fish in the pond have tags. And assuming that my second sample that I collected was representative of the whole population, then this should be the same proportion as the 21 tags that I captured in my 150 fish in my second sample. So I can set up this proportion, and instead of using an equal sign in between, I say, you know what? It might not actually be completely equals. It's going to be really close though. It's going to be approximately. And when I do this, I have figured out I only have one variable. I really want to solve for what that population size must be. So to do that, I need to multiply by n. So I'll get 200 is approximately 21 divided by 150 times n. I can multiply both sides by 150 and get 200 times 150 is approximately 21 times n. I can divide by 21 and get 200 times 150 divided by 21 is approximately n. And when I do this division, I get a value of 1,428.6. Now I know that I can't have a decimal number of fish, so I round that and I say that the population of my fish is approximately 1,429 fish. And I've just used a capture-recapture method to approximate a population of fish. Sometimes we want to know more than just how many people or objects or animals there are in a population. Instead, we might care about some characteristic of the objects in our population. For example, I might want to know what percentage of clovers are four-leaf clovers. To find that out, I don't want to look at every clover in the world. That's just not realistic for cost or time or energy or anything. Instead, what I might do is look at a sample. Right? A sample is some subset of my population. Ideally, it's randomly chosen from amongst the entire population. And what I can do with my sample is then I can count the number of objects that have the characteristic I'm interested in, and from that, I can infer what proportion of the entire population has that characteristic as well. Let's take a look at an example of that. Say I'm working for a light bulb manufacturer, and we've produced a population of 100,000 light bulbs. And before we send them out, we want to know how many of them are defective. Now, to test all 100,000 light bulbs is not a reasonable thing to do. So instead, we take a sample. So I'm going to take a sample of 800 light bulbs. Now, with a sample of 800 light bulbs, it's much easier to test this many light bulbs. You could probably do it single-handedly in a day. So we go through, we test all of the light bulbs in our sample, and we find out that 17 of them are defective. Now, assuming that our sample was chosen in a fair way, and that we just chose them randomly from our population, then we would expect the number of defective light bulbs in the entire population, so the number defective out of the 100,000 total, to be equal to the percentage that are defective in our sample, so the 17 out of 800. Except, again, the same way as last time, we don't want to say that it's equal because it's never going to be perfect, but it'll be close, hopefully. So we say it's approximately. And then again, we do the same thing we did last time, solving for n, our number defective in our population. To do that this time, I need to just multiply by 100,000. So I'll have 100,000 times 17 divided by 800 is approximately the number defective in the entire population. Now, when I do that multiplication, I find that there are 2,125 defective bulbs, approximately, in my population of light bulbs.